Great.
All right, so welcome everyone. Yeah, we should start. So good afternoon.
I don't know why it's still there, but I saw it.
Yeah, can online folks hear us? Okay. Yeah, so my name is Junjie Cheng. I'm an assistant professor at ECE. So this year, this semester, I'm a co-host of the ICON seminar, and this is our first event. Welcome everyone. And today we have Professor Shaoshuai Mo, and he's going to give us his wonderful understanding of the intersection between control and learning, a framework about that. So Professor Mo, he's a social professor at the School of AA at Purdue, and he got his PhD from Yale, and after that he did a one-year postdoc at MIT before he joined Purdue. Professor Mo has received a number of rewards, and he is a co-director of ICON here, and he served also as an interim chair for the autonomous connected system at Purdue. So welcome, Professor Mo, and yeah, floor is yours.
Thank you. Thank you very much, Junjie, for the introduction, and also for ICON the invitation. Good afternoon, everyone. My name is Shaoshuai Mo. Yeah, and
I think we lost your screen online. I think, or at least I did.
Oh, really? Let me check again. Okay.
Yep, now we see it. Thank you.
Can you see it now?
We see your PowerPoint, but we don't see the full screen mode.
Okay, I will do it again for the presentation mode. Can you see it now?
Oh, now I only see a black bar, unfortunately. But I don't know if that's just my anybody else online being able to see the full screen.
It's visible now.
It's visible now.
Yes, now we can see it. Yeah, perfect.
Okay. Maybe I'll just minimize the online windows. We have 54 online attendance. Yes, today we're mainly talk about our progress in the most recent 3 years. It's more than exploration of auto integration control and learning for our autonomous system. And some, I need to record, right?
It should be
Okay. Yeah, I think many of you maybe know that my background is actually in multi-agent system. Digital algorithm for coordination of multiple robots. So this kind of exploration of control and learning is kind of new to me. And also later on, you will see some applications for human-robot teaming. So first, we want to say what do we mean autonomous system and why we care about autonomous system. We can see that actually autonomous systems are everywhere in our daily life, from this self-driving cars to this fancy humanoid robots to exploration of Mars, and also for some collaborative robots, from robotic arm to a large swarm of drones. And so there have been extensive research in this direction of autonomous systems. And with a lot of research going on, there are several fundamental challenges we identified that our group want to pursue for current and future autonomous system. The first one, autonomous systems, we want them to be autonomous. We want to design autonomy for the autonomous system. And basically, we could go in 2 directions. One direction is autonomous control with known dynamics and known object function. The other direction could go from reinforcement learning, which rely on interaction between the system and the environment, and find a control policy to maximize your reward function. Yeah. And also, there are some challenges for design autonomy, especially for all these tasks are usually mission specific. Corresponding to a different task, there must be a corresponding object function for the task. The other challenge is adaptive. We want the autonomous system not just to Like while we're working on that, we'll talk about field adaptive. Adaptive means autonomous systems are usually pre-designed But we want this autonomous system to adapt itself to some unknown environment or environment with large uncertainties or dynamics of the environment. And people could go in the direction of machine learning, but that will require a stage for training using data. For example, for exploration.
That's an issue of new area.
Okay. Yeah. There are some scenarios that we still require a human operator to be involved. And that's why we need to develop techniques to enable autonomous systems to work with humans. What is called co-robots, especially with advanced machine learning AI, people will say, oh, machine learning is more like a black box to us. Maybe we should ask for transparency or insert a little bit of trust to this AI-based algorithm. And whenever it's involving human input, there are several challenges. Like human input are usually sparse because we cannot rely on humans just sitting there to give continuous guidance. And also sometimes most of the time, human input are usually not accurate. And also swarming. Swarming is more like an algorithm to coordinate like a multiple, large amount of like co-rotors, robots, ground vehicles. So the challenge there is each agent, each robot is very low cost, and there's no centralized controller. So in order to address this challenge actually motivated our group's research. We have developed techniques for inverse outcome control for objective learning to learn object functions corresponding to different tasks. We also develop a tunable learning and control framework for this kind of adaptive autonomy. And we also develop a fundamental frameworks for human-robot teaming. And for swarming is actually my PhD research. Is develop a digital algorithm to coordinate multiple agent control, computation, and optimization. So each of the topics is actually not require technical control, also requires this kind of integration of different expertise, like control with data science for object learning, control and learning for this adaptive autonomy, and control plus a little bit of robotics for human-robot teaming, and also control plus network graph theory for multi-agent systems. Today, we're mainly talking about these two, adaptive fundamental framework for adaptive autonomy and also human-robot teaming. Here's the outline. So today we'll present a tunable learning control framework for adaptive autonomy. We basically represent a unified framework which can solve three large classes of problems, like adaptive autonomy, object learning, system ID. This framework is resulted from more like taking differentiation of the Patriarchan maximum principle. We also have extended the framework to incorporate safety constants. And then we'll apply this framework into human-robot teaming. We can directly apply this framework for a robot to take in to human sparse input. And also later on, we develop a fundamental framework for human and robot doing this kind of bi-directional coordination. All right, so let's start from the first part, a tunable control learning framework for autonomy. Before presenting the tunable control learning framework, we think about what do we mean by autonomous system? What are those major components for autonomous system? So usually an autonomous system has three parts. One part is dynamics part. If you have dynamics equation to describe how the state changes with respect to input. And also usually for different missions, this will have an objective function, which characterizing how good or how well this autonomous system perform the task. For different tasks, usually there are different objective functions. Actually, from dynamic object functions, one could to solve optimal control problem to get control policy. Or you will say, in reinforcement learnings, for a system, we don't need dynamics. And we only have control policies, which is determined by the interaction between the system and the environment to maximize the reward function. So for this autonomous systems, its states could be position, velocity, and then could be evaluated under some tasks, some mission, or under some environment. So this is the autonomous system. We think is pretty good, pretty general model for autonomous system. And also then a natural question becomes how to deal unknown components in this autonomous system. There are a lot of techniques. For example, if dynamics are unknown, one could go in the direction of control method from system ID or introduce Kuhlmann operator to approximate the system. Or you could go with using the machine learning like neural network to tune the neural network to map or to approximate this the dynamics. Or if the controller is unknown, one could go with optimal control and adaptive control to achieve a good form of controller. Or you could go to reinforcement learning to get the policy. If the objective function is unknown, which is usually the case for different emissions, one could go with inverse optimal control or inverse reinforcement learning to identify the object function corresponding to different tasks. The method along control direction, machine learning direction, they all have their advantages. Like control method usually model-based, it's more efficient, more robust. Machine learning method usually model-free, it's data-driven, and could allow the system to work to deal with some uncertainty at some level. Then a natural question arises, could we combine advantages of control-based method with data-driven method? This actually motivates our research. The answer is yes. So we want to develop a fundamental framework for autonomous systems to adapt its control and planning according to the real-time data. So we only perform a little bit of change to autonomous system. We insert a tunable parameter to each of dynamics, object function, or control policy. They could have different tunable parameters to allow the system to be a little bit more adaptive to additional changes, additional data. Actually, you could put all the tunable parameters to be one parameter vector theta, and also for each parameter theta, there will have a different system trajectory or different state. And then for the changes in mentioned environment, we could actually model it by this evaluation index, like this additional loss function, to characterizing how well this robotic system perform under this task or under this environment. And then the proposed research becomes, we need to develop a rule to adapt the parameter such that the trajectory of the system states, you could simply look at that. Additionally, optimize the loss function. And this is a very fundamental problem, actually. And before I propose a solution to solve it, I will show you actually first, it will solve the adaptive autonomy part. For example, you could put your changes in emission environment to be this loss function, and then tune this theta to minimize additional loss function. And there's no pre-training is required. Besides that, actually, it could also serve as a framework to solve what they call model-based reinforcement learning. They have some known part in the dynamics and also some unknown parameter in the dynamics with some unknown policy. And this policy will optimize the control objective function. Or they could also solve system ID. For an unknown system, we will introduce some system to estimate this system. We will propose some structure F with tunable parameter theta. And then the loss function will become prediction loss, which measures the closeness of the estimate system to the original system. Or we could also do with solve the inverse optimization problem. Basically, we animate the dynamics or controller from the tunable autonomous system and propose a loss function to measure the closeness of the expert system and the actual system. This is also what we call learning from demonstrations or imitation learning. So all this problem could be solved by this fundamental framework. So next, I will propose to formulate the problem mathematically. So to summarize the problem like this, given a tunable autonomous system, it has the dynamics object functions. And we have additional loss functions to evaluate this system. So the problem is that we want to develop an iterative way to tune parameter theta such that this additional loss function is minimized. But this loss function is a function of its, for example, system states, which comes from this optimal control system. There's obviously a bi-level optimization problem because L depends on she depends on the system, depends on theta. But naturally, one could go the direction of gradient descent. Gradient descent is perhaps the most fundamental method for all kinds of optimization. So intuitively, we could go gradient descent, which required us to compute dl over d theta. Means this is the gradient of this loss function with respect to theta by the chain rule, we know dl over dc because L is a function over G, but we don't know how the system trajectory changes with respect to theta. So this is unknown. Of course, intuitively, we could say, let's just introduce a neural network, right? To approximate the mapping between theta and xi, and then down we'll get gradient. So this, will require a pre-training. And then the question we want to answer is that, is there any way what they call end-to-end learning? Means we want to do this optimization, but we will not introduce an intermediate neural network to mapping this unknown relation. So this is the concept in CSV called end-to-end. And this method with end-to-end learning does not require pre-training and could achieve the dc over d theta directly. So in the following, we'll propose attack this problem more like from the control perspective. So the problem like this, so we want, the system trajectory comes from optimal control system with some unknown parameter theta, but it's still optimal control. So by the Pontryagin maximum principle, one could get a bunch of equations. But what we want is not x. We want is actually get dc over d theta, means the derivative of the state with respect to theta, means how the state changes with respect to theta. So we just intuitively take the derivative, differentiate this PMP, for which we could get this dx over d theta. Actually, we could introduce a new variable. This derivative is something what we want. If we let it to be new state, xt plus 1, of course, all the other also get new state. We actually found that this is a set of PMP for another optimal control system. And this optimal control system could be simply achieved by solving the LQR. So you have a new x, new input, and all these matrices are available. And one could construct this optimal control system by solving this LQR problem. And actually, under this idea, we could achieve, what I call gradient estimator. Means this optimal control system could take the original tunable autonomous system states and input, but generate exactly the gradient. And this is independent of additional loss function. So this actually is a property of the system itself. It provides exact gradient of trajectory with respect to the tunable parameter, regardless whether there's additional loss function or not. This is the property of tunable autonomous systems themselves. And also it can be achieved by simply solving LQR problem. And so under this idea, so we could actually construct what we call a PDP framework. It's feedback framework. So this autonomous system, tunable, and we want to tune this parameter theta such that it stays minimize additional loss function. And we will go along direction of gradient descent. To achieve gradient, this gradient, by chain rule, we need to achieve all this gradient, especially the dc over d theta. So for this dl or dc over d theta, it's trivial from a derivative achieved from the loss function L. But for this, how this system state changes with respect to parameter theta, we introduce a gradient estimator. And this gradient estimator provides exactly the gradient dc over d theta. And this actually, you can find the detailed proof analysis in our unique paper in 2020. And we also students have performed some simulations by applying the framework, solve inverse optimization, system ID, like autonomy, in these three simple examples, like couple multi-link robot and UE maneuvering. It's much faster. This is also what we expected. Control method is, I would say, it's well developed and usually are more efficient and more robust, usually faster than machine learning based, purely machine learning based. Okay, any question? So before we move forward, and also online.
Okay, Shaoshuai, let's see. Can you hear me?
Hi, Bing. Yes, we can hear you.
Yeah, nice homework and lots of question. I think your formulation, you are just looking at dynamic systems with no disturbances. kind of you are treating the model uncertainties as a pure parameterized uncertainty, right? Namely your tunable parameters. So do you have any ideas on how to handle other modeling uncertainties and the disturbance effect?
Oh, it's more here we have not considered being uncertainty actually. It's more like all the uncertainty or the change we could call it changes are modeled by this additional loss function. But of course, you know,
that's something I couldn't understand. Your additional loss function is represent your objectives, but in terms of modeling uncertainties, disturbances, that's what the nature of your dynamic system you're dealing with. So you cannot do. These two cannot be maxed up.
We have not considered the disturbance for them directly to the states or to the original system, but
Okay.
definitely, you know, it's I would say a natural extension to this framework is I would say two parts. First part by ending disturbance and you suggested. Second is that we are not we will not directly employ the states, but instead we will employ output, more employ a linear or nonlinear combination with states and plus disturbance. So that is, I would say, also a natural way to introduce disturbance. But our group, we have not investigated that.
Okay.
Very good question. Thank you,
Okay.
Pete. All right, so we are moving forward. So further consideration or integration, extension of the framework to consider hard constraints for safety. For a tunable system, no, in previous version, we don't have any constraints, but hard constraint also very important for safety. For example, your car speed cannot exceed 200 miles per hour. So we could incorporate this kind of constraints. Same for the task, you also have some hard constraints. So both of them, system safety constraints and task safety constraints, and they are hard constraints which cannot be reformulated as object function. So the problem becomes we minimize additional function such subject to the hard constraint and state from the optimal control system, a constant optimal control. So dealing with a hard constraint, there are two popular methods in control area. First one is reachability analysis, I believe developed by Professor Claire Tomlin. And but that requires then solving HGB. And also there very recently popular method control barrier function, which you requires to find a suitable CBF. So in this, here we want to say whether we could, avoid this method to solve the problem directly. And the challenge here is that, we have been trying to estimate the gradient DC over DC. However, this gradient may not exist at some points because we have this hard constant. So a trick here, we introduce like two barriers for a penalty of the safety constraint. This is a constant optimal control system with hard constant. We introduce a barrier, gamma here, and also a line function to approximate it. So when gamma go to 0, this actually this unconstant optimal control system will approximate the original constant optimal control system. Similar trick we have played for introduce a barrier for the task. So under this, I will apply. You can see that no constants at a no constants, and we will apply the original PDP. This is actually intuitive we have been doing, but the key challenge is we have struggled a lot is that safety guarantee. So question is, introducing this barrier, how could you guarantee that the hard constraint will not be violated? This actually is the part we have struggled a lot. That's why actually if you go to check our paper, it has 44 pages. Most of it are dealing with this part. So we have proved actually when gamma goes 0, epsilon goes to 0, the trajectory will convert to epsilon theta subject to constraints, and also does not violate the hard constraints. We have done some comparison with very popular method. It's called Outro. And for doing, I believe this UAV landing question. And you can see that in their method, it's hard constraints. It violates a little bit. And even for the tilt angle, it also violates. And this is the PDP method. It never violates the constraint. Of course, analytical proving it is another story. And also for complexity comparison, compare that with the 2018 sneak paper called differentiable MPC, but that requires the complexity more complex. is because this differentiable MPC involves computation the inverse of matrix outside proportion to T. Here we don't. So if you're interested, please go to the SIP PDP paper. It's last year's leaves. And summary, we have developed a fundamental framework, tunable control learning framework called PDP, which can solve 3 classes of problem together. The adaptive autonomy, inverse optimization, and also system ID is very simple framework, feedback, closed loop framework. We modeled autonomous system in a very general form, has these 3 parts. Each part has a parameter to tune. And I'm very excited about this gradient estimator because for any tunable control system, this gradient estimator could provide exact gradient of the dx over d theta. X is the states. So, and it's a system property itself, regardless of application. And it can be achieved by simply solving LQR problem. And we have extended PDP to 6 PDP by considering hard conference. And these are more like 2 papers we have published associated to this research. You may ask, what is next? And my background in multi-agent systems. So first, natural extension is that a framework for multi-agent PDP is saying that each agent is a tunable autonomous system with its own loss function Li. And the goal for this multi-agent system is that not tune its own theta I to minimize own object function. And all these theta I is reached to maximize the team reward. So this is more like will appear in this year's CDC. And of course, it's also ongoing with ask when PhD students do this is to introducing data-driven method. It's more like here we assume that F is partially known, but what if F is unknown? So basically you could introduce, any approximation technique. Kuhn operator on introduce another neural network. And some more engineering application, especially human robot teaming, I will show you later how we apply this method to human robot teaming. So before we go to the next section, any questions?
Professor, I have a quick question. So in your work, are theta's parameters that you are introducing, or does the original problem implicitly depend on the theta?
We introduced, for example, that could be, a parameter in controllers. Similar to the concept of adaptive control, they introducing this tunable parameter in controllers, or this could be your dynamics. For example, you could tune the mass of the object by increasing the payload or decreasing the payload. That also changes dynamics. Or you could say more like my object function could also be tuned. It's a parameter introduced artificially for the purpose of adaptive.
So, Professor, if the thetas are injected into the problem to sort of be tunable parameters, I'm trying to visualize like how the safety constraints function G's, how would they depend on those thetas? Are sort of the explicit functions known in this case?
Although we write it here, the safety constraints, there are the safety constraints, but actually, if you say my safety constraint does not depend on theta, it's fine. You don't have to tune your hard constraints. You could delete theta here. Even for the loss function, you could delete theta here. For example, my loss function is x squared. It's just my, for example, it's just my state square, right? You could still say it's function of theta. It's just independent of theta. For any theta, it does not change.
Okay, thanks.
All right, so we will move forward for the applications. Human robot teaming. You may ask, why human robot teaming? This is also a question I ask students in my group. Always first to answer, why you want to do this research? And when upon success, so what? What do you make change? So for human robot teaming, there are several motivations. First, some class requirement. For example, if a robotic arm to help an injured person to wear clothes, requires coordination between robot and human. Second, imitation learning is a very efficient way for program. For example, if you want to program a robot, you just let the human expert to show some demonstrations, and robot will learn by itself. So this is also an area called learn from demonstrations or imitation learning. And also human expertise sometimes matters for complicated mission. For example, a robot wants passing through this area with a lot of obstacles. you could either run a star, D star, RT algorithm for to figure out a way, or you could say if for a human operator, it's very sophisticated. It could just throw out a bunch of waypoints to help the robot navigate. But of course, whenever it comes to a human input, consider human input, there are several fundamental challenges. First, sparse. We really cannot rely on human operators sitting there 24 hours to give guidance. Second, weight. Human operators are not good at generate exact, for example, a correction or input of exact magnitude. For example, I don't believe each of us could generate a force which is exactly equal to, for example, 50 Newton. So magnitude is usually should not be counted as force correction. And also other challenges that we'll talk about later. So first, we will talk about autonomous sparse inputs. For example, for a robot passing through these sophisticated areas, reaching the target points, we want to say human just throw out several waypoints, robot just navigate by following the waypoint. You could say, let's just do a curve fitting. Yes, intuitively, you could do a curve fitting. However, for robots, autonomous systems, they all have their own dynamics. Your curve, the fitted curve may not fit the robot's dynamics. So we really need to tune the robot's onboard planning and controllers to match these waypoints. So this actually you will see all the way the human robot teaming, but actually could be looked at as a problem of robots adaptive to human input. So we have a tunable autonomous system, it's called rotor, and modeled by flow control. Human give some guidance, need some waypoint. And also these guidance are not given directly to the X space, given to its output. Means desired output and time DI. And we could formulate this additional laws as the sum of these errors. More to measure the closeness of autonomous system output and this graph waypoints. So we could formulate our performance index and then directly apply PDP. This is a simple demo, and I believe it's Tianyu and Zhehuan done this. So, for example, give me a quadrotor from a starting position. We want to reach its target position, but this white box represents forbidden fly zone. You cannot pass in this zone. So you could let this quadrotor start flying, it will cross. But we will follow the shortest distance. We suppose the quadrotor has no syncing to the distance. Or, Simultaneously, it's not satisfying my expectation. I will need to give you some waypoint, help you guide you, help you to navigate to avoid this white box. You could also change, once it learned this requirement, you could change the position actually to always follow the waypoint. Then, this is also our paper recently accepted in actuation action robotics. And upon the success in this paper, it gives us a little bit more confidence actually, motivated us to ask what is next. What if human operator cannot throw out a bunch of waypoints? What we should do? So we need to develop a fundamental framework for human robot teaming. To formulate the problem, is actually we need to do some studies about from cognition or neuroscience. First is about their principle of rationality, means intentional agents like optimal control or human operator rational one always aim or tend to choose behavior or design their control or design their state to maximize some reward function. Second, we also want to adopt this concept called human on the loop. This is very different from human in the loop. Human in the loop means all the decisions must involve human. Human is the role. One part cannot be overlooked. Human on the loop means without a human, it can still run, it still makes decisions. However, whenever human want to input their guidance, this robot need to take human guidance. And also some challenges from human. Sparse, weak, and also another one, human operator usually not experts. For a robot to complete some mission, which human can only know whether a robot finished the mission. human does not have any idea about how to characterizing this information by object function. So this is the tricky part. In the previous PDP, for all the machine change, environment change, we rely on to formulate the additional loss function. But for the human robot teaming, you cannot ask the human to write out the object function for the robot to do. Human usually cannot do that. So we need to consider that non-expert human have no knowledge and also no knowledge about robot dynamic model. So this actually gives some requirement for the fundamental framework for us to consider for human robot teaming. First, human on the loop concept, human input are sparse and weak, and also there's no requirement for human knowledge of the robot. Human have no idea what is dynamics is, what is the object function is, what is object function corresponding to the task. So human can only tell whether a robot, goes to satisfy our expectation or not. And we still formulated this, and tunable autonomous system, such that a system trajectory satisfy human's expectation under human's question. So for each tunable parameter robot perform, human will check the robot state. For example, checks co-rotor speed and position. Say, oh, not satisfy my expectation. You need to go a little bit toward east, but I usually go straight. Not good. So human will give some correction. These corrections have no magnitude information, and robot will update again. So the challenge it all comes from the human part. In the PDP, we have additional loss function to serve, as a good measure to measure how close, how well the robot perform. But here, when it comes to human, you cannot ask the human to serve as a loss function. Because human has no idea what loss function is. So this is actually the main challenge we need to consider. That is much more challenging than PDP framework. So it takes us a long time to figure out, but even how to model human satisfaction and correction. Human have no knowledge of J, F, and G. The human input are weak. We suppose human in human mind has a trajectory, although it has no analytical equations, but human could tell difference between the robot's performance and actual one. For example, we want a robot to go to east. Whether a robot goes to east, human could roughly know, right? Whether it goes east. That's the only requirement we require for human. And we suppose actually human expectation is within robot's capability. Means human such expectation of the robot could be characterized by robot object function, tunable object function. Suppose, can see that there is a mismatch between human's expected trajectory and actual one, so human could generate a correction. And this correction is roughly aimed to help the robot to satisfy human. Right? For example, you cannot do this. You cannot say, I want the robot to go to east, but all my corrections help him to go to west. The robot will never reach your consideration. So here we only consider rational players, not irrational players. We assume human's correction satisfies this condition. It's an inner product. So human magnitude does not matter anymore. This is basically saying that human correction roughly help the robot to reach along the gradient direction to reach human expectation, roughly. Actually, if we check these corrections, half of the plane actually satisfy this condition. And the long angle between human correction and also the negative gradient is less than 90 degrees, it will be fine. And also magnitude does not matter anymore because it's inner product. And also it's linear constraints, which allow us to for analysis. So based on this idea, we actually developed algorithm pretty straightforward. This is the part actually we spend most of our time on. And after figuring out this, then done, everything else which follows naturally. For example, we start from a very large searching space, which consists of data sphere. You're going to pick one point. Later on, I'll tell you how to pick this one point. First pick any point, let's say. Robot general trajectory. And then human check, oh, it's not satisfied. And I'm not okay with your performance. Performance does not align with my expectation. Human provides some correction. And under this linear constant, it will help to cut the plane to reduce certain space to be omega k, and then repeat. Proof of convergence. So if robot update the parameter theta k instead not randomly picking this omega k space, but picking at a very special point, which is called the center or maximum volume inscribed ellipsoid. For why this long name comes out, because we will have convergence by proving it actually works. This is our second paper, also just accepted by TRO, which we submitted out the final manuscript like a month ago. Okay, and also this is the simulation. I believe this is done by Zhepui. So basically, we want co-rotor passing through this window. Co-rotor does not have no idea where the window is, and this is actually the vision in the computer simulation. And also, this is one angle and another angle to check whether the co-rotor passing through the window. You can see, without knowing where the window is, robot just will go. It will not pass from this window. You can see ground zero fail, and then it will give some correction. So we really change the color of the correction. It's kind of the blue color. You will tell the robot where to move. The robot will move a little bit. And then give another correction. This is emerging stop. So I didn't pick out this part because it happened. It's in the experiment. No. It's the battery or whatever.
Like in simulation, we'll hit the upper bound of the.
Okay. So after 4 corrections, it were successfully passing through the window. To summarize, we have more like applied the proposed PDP framework for the robot to navigate with human sparse waypoint. And also, we also have discussed this fundamental framework for human robot teaming, which has human on the loop, sparse and weak inputs, and no requirement of human knowledge of the robot. And what is next? We are trying to insert trust between human and machine for the human robot teaming, and also maybe a teaming between a multi-agent system and human. So this actually summarize my talk today. We talk about several things, mainly 2 parts. One part is a fundamental tunable control learning framework, original PDP based on differentiation of PMP, and also extension of the framework to incorporate safety constraints. And we also talk about 2 applications of human robot teaming, robot learning from sparse demonstrations, and also we have presented you a framework for robot to take human guidance, human corrections one by one, called incrementally. And also, besides theoretical work in our lab, we also have some experimental demos. Especially recently, we just got this robust guard. So hopefully, it could work, operate soon to deliver more better demos. This is my lab's website, and also these are 4 papers associated with this today's talk. It's basically 2 papers in NIPS, 2 papers in TRO. And to conclude, I also really want to thank students. This is basically 1 PhD student thesis. It's 4 papers. It's 1 sheet, the post online and UPenn. And also thank Zhepui and TNU for their experimental setup. We also have collaborators for this, and Todd, George, Pavas, Dana, and Sandra. And also thank all my funding agents. And also thank you for your time and for your attention. Feel free to ask any question.
Questions from the audience?
Okay, so Shaoshuai, this being again, yeah, very nice demonstrations. So I'm current. So the one motivation for you to do this one is that like traditionally people we're in different groups, right? So people give the sparse input, and then you are talking about the currently for doing the trajectory planning, they only consider maybe at most the kinematic constraints. So because of that, then your actual drone has dynamics, so it cannot handle it. So that's the reason that you are trying to, in a way, in online or real time using certain just demonstrations get the some information out of the Zoom dynamics, what's feasible with the actual Zoom dynamics. So my question is, how efficient, if or it just say, since we do know the Zoom dynamics, and if I incorporate Zoom dynamics explicitly in my motion planning, will that be a better solution, or just say, sure, it may lack flexibility, but yeah, under certain normal circumstances, it should solve the problem as well, right?
It's hard for me to actually get your questions. It's because can you help me to maybe we're not through the speaker here, through my computer system. It's very blurred.
It's very blurred?
It's more like because we used the speaker in the classroom, and it's very blurred to hear about your question, actually.
Oh, okay. So my question.
Oh, okay. You can maybe you can repeat now. I think I used my computer now.
Okay. So here, right? I think one motivation you mentioned about the what you are doing now is just say traditionally people are just doing like say human operator giving the waypoints, but then just to see the underlying algorithm just doing the pure motion planning just based on kinematics. Because of that, the active Zoom has its own dynamics. So even you have planned trajectories, but the trajectory are not feasible. So that's a reason I see you are doing just trying to, okay, here I have some tunable adjusting mechanism, just prompters, and then you are doing it real time, just do several trial, right? Just to kind of get an influence on what the actual dynamics is, and so that you can accomplish task successfully. So my question is to say, there now we know the Zoom dynamics. Then why, if we incorporate the Zoom dynamics in my motion planning, so it's not a pure motion planning based on pure kinematics. How your solution and going to be compared with that?
Oh, a very good question. The question is, being that as I said, motivation part for applying the PDP to enable a robot take human sparse waypoint. First, I explained if we just do the curve fitting, it does not work because the robot has their own dynamics. So Bing's question is, okay, not just to do the curve fitting, it's say when we do the curve fitting motion planning, we also consider the robot dynamics things. As I would say, our method is one way to solve this, to roughly follow the human waypoint and also consider the robot dynamics things.
That's right.
Yeah.
Hello, Shaoshuai.
Yes. Hi,
Can you hear me?
Yeah.
Hi.
Yes,
yeah,
yes.
This is Wenhai. So, great talk. So I was a bit late. When I joining the meeting, you just started talking about the human on the loop. I heard a lot, human on loop, human in the loop, but I didn't pay too much attention to that. I thought they're saying, but yeah, great explanation on that. So that's kind of clarify some mysteries there. So, but also, though I found it's very interesting, I have a question from I think more from security or safety point of view, right? Because you said it's the object function or the internal, their decision making is completely invisible, right? So basically we treat it as a black box. So in that case, how can human can verify that? So because sometimes we observed maybe 10 times that it's consistent with our expectation, but maybe the 11th time, next time that will go out of our expectation, that it will go wrong, right? So how to verify that in that case?
Oh, summarize, repeat Professor Wen has shown from Paul's question is that, here we only developed mechanism, for example, for a robot to take in humans input, for example, in the learning from a sparse demonstration to navigate roughly following human sparse waypoint. So that we don't have any verification stage, I would say. So when I propose, and maybe it's important that you also insert, human to verify robot performance, right?
Yeah. So because I'm thinking, so this is a black box, right?
Yes.
So yeah, maybe you have very high probability, like I don't know, 80 or 90. So that's gonna achieve your goal, right? But at very sometimes, but when it fails, you don't know.
I understand. Yeah,
yeah, with a very small probability it may fail.
Very good question. We have not thought about that actually, to incorporate this kind of verification from a human, or you could also insert something about I would say V&V techniques, right? You either could check the safety constraints or check whether the robot is actually undergoing my expectation thing. That will be, I think, will be a very nice more further research direction.
Yeah. All right.
Thank you.
Thank you. Thank you.
Another questions from online, from in person? We have 54 online attendance. Plus, I think here is also 50, and almost 100. Any other question?
Maybe I can ask a question. So it seems to me that your framework of tunable autonomous system, one of the key architect in that is that everything is parameterized.
Yes.
So of course, for some of the applications, this parameterization arrives naturally, but some of the applications you really need to assume some family of the function.
Yes.
So are you guys so looking into whether that assumption is leading to some degradation of performance or any sort of performance analysis?
No, it's okay. To repeat Professor Junjie Qin's question about the parameterization, is yes, it's a very good question. We have not investigated that. You could say not everything is parameterized. Especially, I believe in AI and learning, there is a direction called a non-parameterized function, right? So when consider that, I would say if a function is not parameterized, then it comes to very philosophy questions. How should we adapt, make this system adaptive? If it cannot be parameterized by a parameter, so it's I think we can only change it little by little.
Yeah, if you just push to the extreme, you can put a extremely complicated neural network with a huge number of parameters. Then you get in this question of how many data points.
Yes.
So there is all this trade-off.
Yes. I understand. That's a very good question. It's more like there is this kind of I would say it's a major consideration in this non-parameterization function in AI things. It's for practical system, it's a question asked how large the neural network should be to approximate this function, right? Is in terms of layers, in terms of weights. That will be a very good question. Actually, it's very fundamental to investigate.
Other questions from the audience?
Any question from online? I know there are a lot of people here, Aldo and Harsha. This is really you guys are experts on machine learning optimization.
Professor, I have a quick question. So I think that the dynamics that you assume F are sort of can be nonlinear. The safety constraints G can also be nonlinear.
Yes.
Is it possible for the PDP to get stuck in sort of like local minima? If so, then how does that affect the safety property of the system?
Oh, that's a good question. I would say, we use the gradient method. It can only drive you to a point to such that it's reached equilibrium. But whether this point is local minimum or global minimum, that also depends on whether your function is convex or not. So we have not. You could definitely introduce additional technologies to help you to jump out local minimum to global minimum. But that's actually not our focus. But a good question.
Okay, thanks.
If not, we will do the coffee networking thing.
Professor Mo again.
Thank you. Thank you.
We have coffee and snacks. So you guys, if you want to talk, we have the room reserved for 1 more hour.
Yes, yes. You know, for online people, we cannot provide coffee or snacks for you, but still, welcome to attend our seminar in person.
Thanks, Shaoshuai. Great. Very nice.
Yeah, thank you. Thank you. Yes, thank you.
Okay, so
Thanks. Nice talk. Thanks.
nice talk. I think I'm gonna miss the coffee part. We'll get together later.
Next time,
Bye.
Bing. Thank you, Aldo. Thank you,
Thank
Asha.
you. Thanks.
Thank you.
Bye-bye.